Today we're going to talk about concavity, and concavity has to do with the second derivative. So our first derivative is going to give us our slope. So if we have a function f prime gives us the slope. It tells us if the function's increasing or decreasing, which is related to slope. Our second derivative tells us information about the slope of the slope. So a function that has a second derivative that's positive would have a slope whose slope is increasing. So this would be an example of a graph with a second derivative that's positive. We call this graph concave up. Moving along the graph, between these 2 points we'd have a positive slope. But if I move to these 2 points on the graph, I'd have a positive slope that's even greater. The slope is increasing. Another example of a graph that's concave up would be this decreasing graph. Between these 2 points on the graph, we would have a negative slope. Maybe that negative slope would be -2. Further along the graph, we'd still have a negative slope, but it would be greater than the previous slope. Slope might be something like -1/2. The slope is increasing when the graph is concave up. It's the slope of the slope, or the rate of change of the slope. So this graph would also be concave up. F double prime would be greater than 0. And you can tell a graph is concave up. It's kind of like the inside of a bowl opens up. A parabola that opens up is concave up. Any time you have a curve, like an x cubed graph, this part of the graph is concave up, since the graph is opening up. The left-hand side of this graph is concave down. So if a graph that's concave up has a slope that's increasing, a graph that's concave down would have a slope that's decreasing. So this curve is concave down, its slope is decreasing. F double prime is less than 0, that tells us our graph is concave down. So if I pick 2 points on the graph, say here, it'd have a positive slope. If I pick 2 other points, here, it would still have a positive slope, but that slope would be less. The slope is decreasing. So the second derivative is a slope of a slope. It tells us how the slope is changing. Another example of a graph that's concave down would be this decreasing graph. It's like a bowl opening down, or part of a parabola that opens down. So F double prime would be less than 0. This graph, as I said, is again concave down. Let's take a look at the slopes. So between these two points, we might have a slope of, say, -1/2. Moving further along the graph, we have a negative slope with a greater magnitude, maybe -2. Our slope is decreasing. So again, concavity is a slope of a slope. Concave down looks like it's like the inside of a bowl that's opening down, or a parabola that's opening down. Okay, let's go ahead and take a look at the notes and do some examples here. So let's look at example 1. We're going to answer the question about when is that function concave down. So let's first start with a derivative. So y prime is 12x cubed minus 48x squared plus 48. We're talking about concavity, so we need our second derivative. Our first derivative would tell us about increasing and decreasing. Our second derivative tells us about concavity. 36x squared minus 96x, I think I forgot an x here, plus 48. Okay, so that looks pretty good for our second derivative. Let's go ahead and factor it. So we're going to set it equal to 0. Setting derivatives and second derivatives equal to 0 is really important. I believe our common factor is a 12. That's our greatest common factor. So factoring out of 12, we get 3x squared minus 8x plus 4. Okay, so we're going to factor again by doing some guess and check. Well, if my product has to give me 3x squared, I believe it would have to be a 3x and an x. Now we're just going to guess and check with the 4. We need a product of 4 for the constants at the back of these binomials. So we can do 4 times 1, 1 times 4, or 2 times 2. And I believe both binomials have to be negative. Both factors have to have a minus sign in there. So I think 2 and 2 would work, because then our outer product would be 6x and our inner product would be 2x. And then negative 6x and negative 2x would combine to give us 8x. Okay. So let's go ahead and set these factors equal to 0 and solve for the zeros of the second derivative. So when I bring the 2 over and divide by 3, I get x equals 2/3. This one's easy to solve, and I'm not going to show work on that one. So x equals 2. Okay, just like we did previously, where we made a number line for f prime, we're going to make a number line for f double prime and determine concavity. So 2/3 and 2 go on that number line. Let's pick an x value less than 2/3. Zero is always a convenient one to pick. So let's plug a 0 into our second derivative here for x. So plugging 0 into this first quantity, I get 0 minus 2. So that turns out to be a negative. Plugging 0 into the second quantity, I get 0 minus 2, so again a negative. So I get a negative times a negative. Our second derivative is positive, and so our graph of f is concave up. Pick a point between 2/3 and 2. 1 is a convenient candidate. So plugging 1 in here, 3 times 1 minus 2 is positive. Plug 1 in here, 1 minus 2 is negative. A positive times a negative gives me a negative. So since our second derivative is negative, f is concave down. Okay, let's pick a point greater than 2, say 3. Inputting 3, we're going to get a positive and positive. So positive times positive is, our graph is concave up again because our second derivative is positive. I forgot to tell y'all one thing. These are not called critical numbers. They're called possible points of inflection. They're possible points of inflection until we look at our number line and check to see if our signs change on our second derivative. So at our number line, we can see that the signs change from positive to negative at x equals 2/3, and then again from negative to positive at 2/3. So these possible points of inflection, upon inspecting the number line, they get upgraded from possible points of inflection to actually full-blown points of inflection. So we can get rid of the extra p there. They're points of inflection. So let's go ahead and answer our question and justify. The graph is concave down. We use parentheses with concavity. So concave down with parentheses 2/3 to 2 because f double prime is less than 0. It's probably the easiest one to write down the answer to and justify because we're always using parentheses and the justification is just very straightforward. Okay, let's do example 2. Okay, so we're going to first identify that they're wanting us to talk about concavity in the answer and points of inflection. So we're going to need our second derivative. So starting with f prime of x, we get cosine x. Our second derivative is going to be negative sine x. Set the second derivative equal to 0. And we're going to find our possible points of inflection. So we're going to look between 0 and 3 pi. When does sine equal 0 between 0 and 3 pi? Well, at pi and at 2 pi. So those are our possible points of inflection. We're going to make our number line. Make sure you don't put arrows on the end because we're not going all the way to infinity and negative infinity. They've limited it this problem to the interval 0 to 3. pi. So here's our number line. Let's make sure we put f double prime to remind ourselves we're testing in the second derivative. So let's pick a value between 0 and pi. Pi over 2 is a convenient one to pick. So we need sine of pi over 2. Well, let's think about the unit circle. Pi over 2 is right here. Sine of pi over 2 is 1. So that's positive, but times the negative in front of sine, that gives us our second derivative that's negative. So our graph is concave down. Picking a point between pi and 2 pi, 3 pi over 2 is a convenient one to pick. Down here, sine would be negative 1 times the negative in front in our second derivative gives us a positive value for our second derivative. So the graph of f is concave up. And then lastly, picking a point between 2 pi and 3 pi, well, that takes us all the way around the unit circle, and we'd be back over here to an angle that radians measures is equivalent to pi over 2. So pi over 2 has a positive value for sine, but again, because of the negative in front of the second derivative, our second derivative is negative, so our graph is concave down. So let's answer the question that we're given. Determine the intervals where f of x is concave up in justify, and give any points of inflection. Okay, so the graph of f is concave up on the interval pi to 2 pi because f double prime is greater than 0. Let's give any points of inflection. We're going to justify these. Even though it doesn't say to, we're going to. So point of inflection happens when the signs change on the second derivative. There are points of inflection at 0 and 3 pi, but we don't have enough evidence to answer that. So we're going to only look at our number line and see where we actually have evidence that the sign of the second derivative is changing. So at pi, there's actually it doesn't ask for the x values of the points of inflection. It actually asks me for the plain old points of inflection. I'm going to try to delete this off of there. Okay, just a little bit of delay here. So the point of inflection happens at pi. I need the y value for the point of inflection, so I'm going to go back up to the original function and plug in pi. So going back to the original function here, sine of pi is 0, plus 2 is 2. Our other point of inflection happens at 2 pi, and we need the y value, so let's go back to the original. Sine of 2 pi is also 0, plus 2 is also 2. So let's justify these. The first one is a point of inflection, because at that point, f prime changes from negative to positive. The second one is a point of inflection, because f prime, oh, you know what, I'm sorry, because f double prime changes. So go back to that justification, change it to f double prime. And this second one is a point of inflection because f double prime changes. Let's go to our number line. Our second derivative changes sign from positive to negative at 2 pi. Okay, that's all the notes that we're going to do on this. So go back and watch it again, pause it until you understand about concavity and points of inflection.